talking about Fourier transform bounded kolmogorov complexity. I think Mohammed here.
Thank you.
Yeah.
Hi, everyone. So I'm going to do a nice lighter talk, perhaps before lunch, perhaps, and just about a paper a couple years back that I did on approximating kolmogorov complexity using the Fourier transform. And so this is also co-authored Professor Simon O'Keefe, my supervisor. And so the motivation for this was to do with my main area of study, which is emergent properties and emergent phenomena. And in cellular automata, particularly one-dimensional variant, where it's just a lattice, and in its simplest case, the elementary case, where it's just binary, you have over time this two-dimensional image or space-time that gets produced by the dynamics. And Stephen Wolfram, he's obviously produced the most famous or popular classification of elementary CAs, where you've got the 4 different classes, the low complexity and the high complexity. And the emergent phenomena typically tends to be around class 4, which there's been, coined the edge of chaos, but you've got class 3, which is chaotic. And so his classification was obviously done by eye and over a lot of simulations, and how things, his heuristic classification, obviously, he supported by the fact that, how things look to our eyes and our innate pattern recognition ability is quite powerful. But obviously there are some, it's incomplete and insufficient because of this method. And so, especially if you want to automate a way of finding these dynamics. So this is what prompted then me to create 2 metrics. One of them, or not new metrics, but the direction of Kolmogorov complexity to identify the low complexity classes 1 and 2, and the high complexity classes 3 and 4. And then once I have that, then I use the 0-1 test for chaos in a separate paper that's done to distinguish between the chaotic classes and the non-chaotic classes. And in particular, then I can isolate the high complex non-chaotic dynamics that should contain the emergent phenomena. So that's the motivation behind this paper anyway. So just a very simple definition here. So Kolmogorov complexity obviously is it's a powerful and elegant definition. It generalizes the Shannon entropy in ways to allow it to be applied to dynamical systems. And it's a nice, precise, objective way of quantifying information in objects, use it from an algorithmic point of view. It's defined as the length of the shortest program that can generate a given string and halt on a universal computer. For example, if you have, and the intuition behind it is obviously the simpler sequences are described with shorter programs because a lot of repetition perhaps, and you'd have a very simple program to describe that. And that simpler program then results in a smaller complexity algorithmically. So using compression. So the compression is obviously useful for reducing space, bandwidth for image storage, transmission across the internet, especially relevant for data to train machine learning and other applications. But it's a good approximation for program size, and it's traditionally the way you approximate algorithmic complexity. General lossless compression algorithms is the way, because Kolmogorov complexity obviously is not computable in general. So again, regularities can be used to compress descriptions, and so that higher compressibility approximates to lower complexity, right? So that's the idea there. Very just a bit of background. Then you have in broad, right? So in broad, you can categorize compression into 2 versions, lossless and lossy, where the lossless compression you require for approximating Kolmogorov complexity, and also it's sometimes like a legal requirement for medical images in diagnosis, for example. But over the majority of the files transmitted over the internet are lossily compressed. So these are used in these are cases where a small bit of error, it's acceptable trade-off for a higher compression, because for lossy compression you can have a higher compression rate than lossless, right? Like for example JPEG. Yeah, and so let's not go too much into that, but we define lossy compression as after you've decompressed it, you get back the original image plus some error. So yeah, the existing loss and compression methods, there's many. A lot of them can be used to approximate kolmogorov complexity, and that's where I began. Obviously, entropy encoding, Huffman encoding, run length encoding, Lempel-Ziv-Welch, all these are fine algorithms to use. And they're successful at compressing large regions of uniform and repetitive behavior. For my particular case, a lot of them fail to compress sufficiently irregular patterns or more exotic symmetries, such as self-symmetry. Typically, for example, in this the Sierpinski triangle, you got a lot of you got the triangle, and then you got a smaller version of the triangle, so different scales of the same pattern. These types of symmetries there, and other features found in fractals. And most are designed to compress one-dimensional data sequences, obviously, so they're less suited to things you find like nested structures, patterns that are only distinguishable in their natural dimension. And so obviously inaccuracies in compression lead to poorer approximations of complexity. Here on the right here, you've got an example. This is the run length encoding of just on the left, you have the original space-time image, and on the right is the run length encoded. And you can see it's not sufficient at compressing triangular structures, for example. Right. Yeah, the two-dimensional Fourier transform. So the discrete Fourier transform, or 2D discrete Fourier transform, is responsible for transforming an image from the spatial domain into the frequency domain. And it does that by decomposing it into complex valued coefficients with real and imaginary components. So you, let's say, yeah, I wanted to just see some of the notes that go with, but okay. Yeah, the Fourier transform is a fundamental operation in digital signal processing. It's got a wide range of applications, and it's a popular image compression technique. Unfortunately, it's lossy in nature, and I'll go into show how that is the case, which kind of excluded it as a candidate for approximating complexity at first. But the power of this transform is that it's able to discover hidden patterns via its convolutional properties. So it's often, so it can transform, seemingly arbitrary data into a more efficient description by identifying these intrinsic patterns. So that's the motivation here for perhaps it can encode these space-time diagrams more efficiently and lead to better compression. And it's an invertible function. So on its own, it doesn't lead to any loss of information, the Fourier transform on its own. When all of its yeah, so that's fine. So traditional frequency filtering, the way it works is you have filter Fourier coefficients for a simplified or a lossy compressed version, representation of the original data. So the image is transformed into the frequency domain, and there you filter out certain frequencies, and these frequencies are negligible in general because the appearance doesn't seem to change that much. The Fourier-based compression encoder uses a binary mask to do that filtering. So it will mask out some of the coefficients which correspond to those frequencies. And this masked out version will be the minimal representation, the compressed representation. So when the coefficients get filtered out, certain information is discarded, a loss results, and therefore that's how you get the lossy compression. That's with traditional Fourier transform-based compression, and that's why it's lossy. And the thing to observe about the coefficients are the majority of the useful information gets encoded, and only a small minority of the coefficients, a lot of them can be discarded in this way without a noticeable difference in the quality. But that's just something to note. Right. And this is an example, yeah, the image up here shows an example of the Fourier transformed image, and on the right is a mask to filter it, where the black is the zeros and the white is the ones, for example, so where it's let through. So only the coefficients in the center of this two-dimensional transform are kept. Right. So how do we extend this then to lossless compression? A lossless Fourier filter will mask the coefficients, right, and remove negligible information to maximize the compression in such a way that the resulting construction is identical to the original and it has no loss. That's what we're going for with the lossless Fourier filter. So the same thing as a normal filter, except the final resulting reconstruction is lossless. The definition here, so we have a set of lossless filters, which we call big M, and which modify the Fourier representation without preventing it from reconstructing any original image exactly. Right, so that when you decompress the masked Fourier representation, it reproduces S, the original S. Right, that's what we describe here as a lossless filter. An example of a trivially lossless filter, for example, would just be all ones. M1 would be a filter of entirely all ones, and it's lossless, but it's trivially lossless because there is no loss, because it keeps all the information by avoiding any filtering of coefficients and compression. So that's just a very simple example. Now, that would have probably been the only type of lossless filter you could have but there's this trick that happens with you use quantization to do denoising. So the Fourier-based decoder, so you have a decoder, it then further binarizes this reconstructed image, right? So we define the decoder, the inverse of the compression, as the inverse Fourier transform with an indicator function, the binarization step. And this binarization step maps real values to binary values just using a threshold. So anything above some real valued threshold gets mapped to 1, and anything else gets mapped to 0 otherwise. But the power of this simple quantization step or binarization step, it actually usually would introduce more error, but rather than introducing further loss, this quantization effect actually removes the noise in certain cases from certain types of lossy reconstruction. So it can be used to denoise and then retrieve the original image to have a lossless reconstruction. The error correction, right, it only applies to a certain not all cases, but you can kind of get an intuition for why this might work. At the top, there's an original with all ones, and then you might have a lossy reconstruction where it's got 1.5s everywhere, and then this binarization step will just map those 1.5s back to ones, and therefore you retrieve your lossless, you retrieve the original image. And this is an image below it of a space-time diagram that is, you can see, has got some loss when it's reconstructed using the inverse Fourier transform. But then when it's binarized, that becomes the original image again, and it's denoised or error corrected. So essentially, this denoising step allows the discrete Fourier transform to be extended to a certain range of lossless compressions now, other than the trivial case. You have a certain range of masks that you can use that will allow for lossless reconstructions. This is perhaps just to put this visually to see this in action, you've got on the left here 2 examples. On the left is the original space-time dynamic. On the second image, you have the Fourier transform of that, a 2D Fourier transform of that. On the next image along is the filtered transform, the optimally filtered ideally. So you've masked out as many coefficients as possible. And the next image along that is the reconstruction, the lossy reconstruction using the inverse Fourier transform. And then the quantized or the binarized version is the final image where it retrieves the original binary image. Now the step here is the optimal lossless Fourier filter to search for that, which is able to filter the most coefficients, so maximally compressed representation, without the loss of the reconstruction becoming too noisy to be error corrected via this quantization effect. So on the extreme cases, you have your trivial lossless filter, which is all 1s, and on the other end, you have all 0s, which would produce, which would lose all the coefficients, all the information, and you'd have a lossy, you wouldn't retrieve the original image at all. Somewhere in between there, you're going to find your filter, which is still lossless and yet masks out the most number of coefficients and will produce the smallest compression for that particular image. And that will vary dependent on the specific input itself. So for simpler ones, you can get more filter. You can filter out more coefficients, and it will not be sufficiently noisy to retrieve the original. For more complex, that's less so the case, and it ends up being that the size of the mask itself is the is almost parallel to the size of the representation. And so, yeah, this is actually an optimization problem. This is the part where you have to search for the filter, the optimal filter. It's not trivial, but you can just use, for example, a greedy search algorithm. You can use a slightly better version, and this will be the bottleneck for this approach, how good your search is for this filter. For example, I just described very basically the greedy algorithm would be you start with all 1s, and this your size, and then you decrease it. So you then go through all the masks with just a single coefficient masked out, single coefficient with 0, and you do all the variations there, and you ensure that all of them are still lossless in the end. And then you keep on adding to that size another 0, until you get to a point where you are unable to reproduce a lossless reconstruction. And at that point is the point where you have the minimal the filter with the minimal size, because any more than that would be lossy. Okay, so this is everything in order now. You have the original image on your left, which is called S. We Fourier transform it. It becomes a representation. Then you do an optimal compression filter, M star, and that becomes a compressed representation. You do the inverse transform, you get the lossy reconstruction, and then you denoise it by quantization, this binarization step, and then you get the lossless reconstruction at the end. That's the entire process there. And we say that the size, so yeah, the optimal filter is defined here as the lossless filter resulting in the smallest Fourier representation, and the size, we measure the size here as the number of non-zero coefficients. So sparse representations will have a smaller compression size. Then we say lossless Fourier-based compression opens up the potential for a Fourier transform bounded kolmogorov complexity, which is can be useful for other things, where the program is the filtered Fourier representation, and the program's length becomes equivalent to the compression size of that filtered representation. And the computer is almost like the Fourier-based decoder, in this case, C. Yeah. There are some related research that I found later that this is almost parallel to with lossless wavelet transforms. You have parallel in lifting-based lossless transforms, which use wavelet transforms and quantization to again produce lossless compressions, you have the input signal, which is transformed using wavelet transform. That gives you the representation. And then the resulting coefficients, instead of being filtered, are quantized at this step. So they're rounded, the values are rounded to integers. And that compressed representation is then that quantization to the representation introduces the loss that corrupts the invertibility of the transform. So the inverse no longer guarantees an exact reconstruction, so it's lossy. But then a final step of a reversible denoising or lifting step is used to remove that loss. So in that case, that's where they do a search for the optimal denoising filter. So again, there's a search for a filter, but it's almost turned on its head in this case, where the quantization is used to compress and the filter is used to denoise, as opposed to where we use the filter to compress and quantization to denoise. There was it's just found independently, this line of work. So the strengths of using this the Fourier transform for approximating. It was shown using other lossless compressors such as run length encoding, LZ, zlib, glib, and bzip2. Some of these compressors were compared and on 3 different tests, and it was shown to outperform them, particularly for these space-time dynamics as well, so 2-dimensional data. It has a strong Pearson's correlation to them as well. That's shown down here, where the most different was run length encoding. And there was this interesting symmetry-based test that was done, where the idea here is you apply different symmetries to 2-dimensional images, such as rotation, inverse, the inverse. And so the idea is you should get the same complexity measure across all of these symmetrical data sets, and any difference can be attributed to the imprecision in the metric itself. And so it was shown to be more consistent to a lot of the compression metrics used. One of the ones that was not using compression at all, it was the block decomposition method, which is approximates kolmogorov complexity with using the frequency of the occurrence of the string as opposed to the compression. So that was also used too. And some of the limitations, obviously, is that the discrete Fourier transform is a powerful method, but not for all. It's not ideal for all types of data. For example, discontinuous or non-smooth. It's not good. You can imagine the square wave uses an infinite number of coefficient frequencies to be able to encode it. So in that case, it's not an efficient way of encoding, whereas you could just use half on, half off as a more efficient representation of that. You have binary information is key for the DFT to compress losslessly. So it's shown the limits of, so the range of values you can error correct for is dependent on that threshold value. And yeah, that therefore depends on binary information to be the original image or original data to be binary. The search algorithm as well is a point where it could be inefficient or impair compression if the search is suboptimal and you don't actually find the optimal lossless mask. So those are some of the limitations of that. And yes, I think, and this is just the final step, just showing you the range of space-time dynamics you get from simple for very low complexity to very high complexity. At the far end, with the high complexity, you have a random space-time. So it's actually not a space, it's just a random image. So that's the maximal. And on the other end is just all zeros. And in between that, it's varying complexities of space-time, which kind of agree with our visual inspection of it. And that's that. Yeah. That's the last slide. Yeah.